Why was this delayed? Lab 4.
Lab 4 is due initially I was thinking due the Monday after Thanksgiving. But I want people to enjoy Thanksgiving, so I make it due on Tuesday. So give you one more day. So we will be talking about that today. But I really want you guys to work on transactions because it's really important. So, sorry about that. But I know people are busy with the final and all that stuff, so it's really tricky. All right, so hello, yeah. So before I started the lecture today, I'd like to do a quick survey among this class. So I have just released Lab 4, which is core optimization, right? Which is, in my opinion, a really interesting project, right? Basically, it tests on your understanding of the core optimization stuff we talk about. And if you look at the way it's really useful for me to show this assignment. So what this one does is, so the outline of the core optimizer is as follows. Basically, it follows exactly the same sequence of discussion we had in our lecture slides. Okay, so we start with an overview of the core optimizer. And this diagram looks maybe complicated, but essentially it is the same high-level diagram I showed in lecture slide, which is you have a plan generator, a statistical catalog manager, and then a cost estimator that runs between the two. And then you basically iterate through this loop of producing a new plan, estimate the cost, and iterate through this loop until you settle on a fairly good plan at the end of the day. So the first step is to do what we call statistical estimations. And this ties with all the discussion we had about building histograms. And as well as if you do not have histograms, how do you estimate the selectivity for a particular type of query, whether it's join or whether it's selection. We talk about those in our lecture slide, right? And it gives you a very simple formula to estimate the cost of a particular join query, right? For example, if your join is a sequence of join like that, T1 join is T2 join, and so on, join with Tn. If you are going to use a lefty tree plan with the order that's given, the cost is simply this. If you look at it, it's simply scan table T1, scan table T2, the join cost between T1 and T2, plus scan T3, and the join cost of T1 join T2, then join with T3. What that essentially tells you is it's basically a lefty tree plan, right? Basically, Right? That's essentially what it does. I scan this, the join cost, scan this, then the join cost of this. Right? Essentially what that formula tells you is essentially you're using a left tree plan to perform U-join. And in this assignment, we make it really simple for you to ignore the fact that you may have different join algorithms for the join operator. So we simplify, you optimize it quite a bit. You don't have to worry about that. Rather, you only need to optimize for nested loop join. So we tell you that the join operator is going to be a nested loop join. So you only need to optimize for that. Does that make sense? This dramatically simplifies the job of your optimizer because you don't have to worry about what if I use hash join, what if I use page nested loop join, what if I use block nested loop join. You're always going to use simple nested loop join as your join operator. So, which means to estimate the cost, it becomes really, really simple. And then you talk about how you do selective estimation. There's a lengthy discussion here, but if you have followed the discussion from my lecture, you can safely ignore this. Essentially, we're asking you to build an equal width histogram. Essentially, that's what we're asking you to do. You don't have to worry about equal depths, nor the variance optimization histogram we talk about in class. Those two are more sophisticated than equal width. Equal width is the simplest form of histogram you can ask for, and that's what we are asking you to implement for this project. Okay? And that basically gives you enough background for you to implement access1 and access2. Basically building a histogram, scanning table to collect statistics such as mean value, max value, distinct values for a particular attribute. And those are those catalog variables that we need to use in selective estimation, right? So as we show in lecture slide, the correct lecture slide. Then we talk about the cardinality estimation for join. This basically follows the similar discussion we provided to you in lecture slides, right? The number of keys from one table multiply the average number of values per distinct value from the other side. That gives you an estimation for the join cardinality, right? We'll talk about that in class. And lastly, the last exercise is about ordering your join, right? So if you have T1 join T2 until Tn, rather than do it this way, maybe you should consider a different order, but still limit yourself to only left tree plan. There's a system test for this where we give you a particular join. If you use the input order as it is, your join will not be able to finish in the time we specified in the system test. So system test will fail. Unless you, of course, you can quote unquote cheat your way out by using a supercomputer like really, really fast. Even for any strong order, maybe you can finish before the specified deadline, right? Time budget. But on typical computer, we did a lot of tests. If you use a typical computer and you don't do any join ordering optimization, you just use the order given from the input, you won't be able to finish in time, specified by the system test. So this join ordering, and what this ordering does is essentially the greedy algorithm we introduced in class. You look at the best one relation plan, best two relation plan, so on and so forth. Then you will end up with a reordering of your join that will, if you reorder your join using this algorithm, still using nested loop join, by the way, you will be able to pass that system test. Of course, let me tell you, do not try to mess with the code, because another way to easily pass the system test and cheat your way out is to simply change the test to use hash equal join instead of nested loop join. Then once you change hash equal join, the ordering of the join doesn't matter anymore. I mean, it still matters, but with respect to the system test we have set up, we set out a particular time budget so that if you use nested loop join, using the given order, you won't be able to finish. But if you change to hash equal join, using that order, you will be able to finish. But join ordering optimization for hash equal join still matters, because even if you use hash equal join, if you do this ordering, you will find an even better order that will be even faster than the default ordering. It's just that the default ordering, if you use hash equal join, will still give you a sufficient enough running time to pass that system test. So do not try to change code for that. Make sure you use just the join. Basically, there's one line called initiate join operator. You should use join instead of replacing this with hash. Some of you might have changed this from join to this when you did your lab 3, right? In order to get really good running time for your context. If you have done that, make sure you change back to this. Otherwise, all your optimization code become irrelevant for lab 4. Does that make sense? Yeah? Okay, cool. So that's it. I mean, that's lab 4, and we give you about 2 weeks. Of course, in between there's the Thanksgiving holiday. I don't know how you view this. Maybe it's a few days you can work on your project, right? So I think nothing is good. But on the other hand, I know you have obligations. You have to visit your family, enjoy your Thanksgiving dinner, all that stuff, right? So that's why initially I set the deadline to be Monday, which is right after the Thanksgiving holiday. And I thought about it, I should let you guys enjoy the Thanksgiving day. So I make the due date on Tuesday, give you one more day. To some of you, lab 4, sorry. Now, before I proceed with today's lecture, I want to do a poll to understand what people want to do, okay? We are down the way, right? We are really close to the final. I'll give you 2 options. One is we do only 4 labs, meaning this will be the last lab, and there will be one more homework assignment, by the way. Written assignment 4, that's on transaction, which I will release on Thursday after you turn in your written assignment 3. That's it. On written assignment side, that's about it. On the live assignment 1, I have 2 options for you. Okay. One is we keep 4 labs, and this will be your last lab. So we won't be able to do the transaction lab, which I really, really want you guys to work on, because that's a really important piece of David's kernel. And we keep the distribution of the grid as it is, meaning 50% to project, 10% to homework, and 40% to the final. And final will be basically covering everything from your homework assignments and open book. Okay? So if you feel comfortable doing homework assignment, you should have no trouble in solving the final problem. So that's option 1. Option 2, I will assign lab 5 on transaction, but then it will probably due right around the final week, given the time of it, right? But in exchange, what I will do is I will increase the portion of your project to 60%. Homework only 10%, and final will be reduced to only 30%. That make sense? Option 1, option 2. Option 1 is 4 labs, weight distribution, the correct distribution as it is. Option 2, 5 labs, 1 more lab. But I will increase the weight of the product, reduce the weight of the final test. So,
how big is the last one?
How big? I will show you.
Because mine was on the 12.
Lab 5 is not, if you understand transaction concept that I have discussed and I will be continuing discussing today, Lab 5 actually, in my opinion, is easier than Lab 2 and 3 and 4. It's probably around the same level of difficulty compared to Lab 1, if you ask me. So it's not too bad. On the other hand, are you willing to bet you're going to do really well in the final, right? Because if you go with the option as it is, final is 40%, right? So you're going to bet that, first of all, I will be really nice, give really not so difficult question in the final, and you will do well. On the other hand, if I do give you another lab, that's something you can control, right? Because you work with your teammates, and if you do well, so far, from what I can tell, most of the team got really good grade on your lab assignment. Does that make sense? So you are better off in option 2 if you think your performance on your lab assignment will be better than your performance in the final, right? Suppose you get about 90 or above in your lab, and if you think you can score 90 above in the final, then you should keep option 1. Otherwise, you should consider that option 2. Right? That's my rationale of thinking about this. Personally, if you ask me, I prefer to go with option 2 for the fact that I don't want to place too much weight in one final test. If you screw up big time. For that reason, secondly, I feel being able to work on the transaction model is important for you to understand really, because once you do that, you can safely claim after this class, I feel comfortable building Oracle from scratch because you know everything pretty much. Seriously, you are better off than most database engineering outside this classroom already if you finish that file. All right, so that enough said. Let's do a poll. Okay.
What about, if it's option 2, what about a written version 1?
Written assignment is not affected. There will be still one more written assignment, of course. All right, how many go with option 1, which is keep the way it is, do not assign me another lab, and 40% of the time. Okay, all right. She must be really good at this test, I think. And how many go with option 2? Let me repeat, just confirm before you vote, right? Make sure you know who you are working for. Don't just go and say, oh, all Republican, all Democrat, I don't care who the name is. Just go there and Republican, Democrat. You have to know the candidate you vote for, right? Option 2, reduce the final weight to 30%, but then allow me to assign you another lab 5 on transaction. With understanding the due date will be around the final weight time. Okay, how many vote for option 2? All right, option 2 it is, okay?
I don't know if this is possible, could you maybe release that lab early?
Yes, I will release, I have the lab ready, actually. So I will release, but I don't want to give you guys too much pressure, right? So what I will do, I will release the lab 5 next week, before Thanksgiving, so that you have the option of start working on that once you are done with lab 4.
Because then we can get it done early.
Yeah, sure. Yeah. I think that's definitely an option. That's definitely reasonable. Okay, so that's it. Right, 30% for final. That way you don't have too much pressure coming to final. And plus, final is open book. Similar type of question to your homeworks. So if you can do your homework, or if you haven't done your homework, but you can understand the solution I posted, you should be fine. Of course, if you haven't done your homework, you lose 10% of your price, right? Or you have done your homework, but you really didn't think through it. You just write out whatever you know and didn't really pay much attention to it. Yes, you still got 5% credit over there. You lose about 5%. But as long as you make sure you understand the solution I have posted, can work your way out yourself with reference to that solution, you should be able to do well in final as well. Okay? All right, so that being said, let's continue with the lecture today. Okay, so we talked about transactions, the overview of transactions, and I talked about, we spent quite some time on isolation levels, and I use this particular example to show you the difference between So we talk about transactions, and I use this particular example to show you the difference between serializable isolation level and repeatable rate isolation level. In particular, for this particular setup, it is not in serializable isolation level. Why? Because at the end of the day, the state you reach is not the same as if you do T1 then T2, nor T2 then T1. That's why it's not serializable. But at the same time, it is a repeatable rate because there is no delay rate, and item read multiple times by one transaction do not change value. Right? Item read multiple times by the same transaction do not change value. So it is repeatable rate. What this simple example illustrates to you is that two things. One is repeatable rate isolation level indeed is a relaxation of serializable isolation. Secondly, repeatable rate isolation level does allow more degree of concurrency concurrent execution in your scheduling of different transactions than, of course, serializable isolation levels. So in practice, as a database administrator, what would you do? Well, you look at your particular application. If it's a really mission-critical application, like banking transaction scenario, you go with serializable isolation level. But if it's like more like student admission and things like that, it's fine if you see some glitch by some user. For example, this user might be puzzled, saying, "Oh, why I'm seeing different output when I execute the same query twice when I'm still in a transaction?" If that's important to you, then you should not go with repeatable wait. But if there is some leeway there, and you expect your user to be able to comprehend that, repeatable wait is the way to go. Because it does allow more degree of concurrent execution of your transactions, which means higher throughput, better performance of your system. Okay. So so I will skip this slide. We spent too much time on that example, so I will just skip that. And one observation is that from that running example is read-only transactions really helps optimize system performance, which is not really that hard to understand, right? Because if you only have read-only operations in a transaction, you are not making any change to the underlying database, then you are not going to interfere with the execution of another transaction. So read-only transactions are really your friend from a database kernel point of view. So the standard is serializable isolation level, and in practice, people design different weaker isolation levels. We talk about repeatable rate, but in practice, if you go to any commercial database engines, the industry standard is to have 4 different isolation levels. We covered the bottom 2 in terms of the level of isolation they can guarantee. Serializable is the strongest. Repeatable rate is the second strongest isolation level. Then there are 2 more isolation levels that typical commercial database engine are able to support. And in most cases, by default, people go with either serializable or repeatable rate. That's why I cover these 2, and the other 2 I leave for yourself to explore. You can, if you're interested, you can just Google online and look through what the other 2 isolation levels are. But typically, people go with either serializable or repeatable rate. Okay. Now, coming back to the general concept of transactions, we said this multiple times. It is a sequence of one or more SQL operations treated as an atomic unit. And it supports both concurrent execution and crash recovery from failures. So in particular, transactions in a database support the following properties. The so-called ACID property. This is extremely important. You need to remember this. So that whenever others ask you what database can do, this is something that you should reply to them, right? It guarantees the important ACID properties. What are the ACID properties? A is atomicity, which we have explained already, right? All or nothing semantics, right? Consistency, which I will discuss in the next slides. Isolation we'll talk about, right? We just explained what isolation is. Basically, what isolation says is that even though there could be multiple concurrent execution of multiple transactions from multiple users, but from each user's point of view, it's like your transaction is running in isolation. You don't have to worry about the fact that there are some other transactions being concurrently executed at the same time alongside with your transaction. Right? So that's the concept of isolation. And durability and atomicity actually go together, right? Because it's all or nothing. Right? Durability means that if a transaction has committed and if your system has crashed, after that, then all the changes made by that transaction should be persistent to your database. You may wonder, isn't this automatically true? When transaction has committed, all the changes made by that transaction will be permanently reflected to your database. Well, this is not true by default. I had a simple argument I showed you, I believe, either last lecture or the lecture before last lecture. The reason is you have a buffer manager sitting between your transaction manager and your non-volatile storage media such as disk that's stored there. The changes made by a transaction are only reflected to dirty pages in your buffer. And when the transaction has committed, that only means all those changes are reflected to those dirty pages in your buffer. It doesn't necessarily mean those dirty pages have been pushed back to disk by the buffer manager at the time the transaction has committed. Of course, you can simply make an adjustment saying that, okay, fine, what I will do is whenever a transaction has committed, I will ask the buffer manager to push all the dirty pages caused dirty to be caused dirty by this current transaction, and I push all those dirty pages to the disk. That way I can ensure durability. Yes, that's a baseline solution. However, this baseline solution could be really expensive because you are really interfering with how buffer manager works. You are basically saying whenever a transaction commits, you need to push all the dirty pages to the disk, rather than the normal way of buffer manager. The way it works is to only push a dirty page to the disk when it is a candidate for replacement, determined by whatever buffer replacement algorithm the buffer manager decides to use. So later on, we will talk about some different variations of this baseline algorithm that shows much better performance in practice. Okay? So those are the four properties. I think we have a fairly good understanding of atomicity, isolation, and durability. The only thing I need to explain to you is consistency. Right? What does it mean by ensuring consistency in a database engine by the transaction manager? So isolation is achieved by logging, which I will having a detailed discussion right after this lecture slide, so I will skip this part. Durability is achieved by logging. Again, we will come back and revisit this part. Same as atomicity. Okay? So just keep in mind, isolation is realized by using logs. Durability and atomicity are managed by logging, which again, those I will discuss them in details in the follow-up lecture slides. So now let's talk about consistency, right? What does consistency mean, right? So consistency means the following. For every single transaction, you must assume the following, which is all the constraints defined by the functional dependencies, right? I hope you, we didn't discuss functional dependency in this class, okay. All right, so functional dependency is something I covered in my undergrad database class. We didn't cover it here. But what it says is certain constraints that your database must satisfy. For example, I'll give you one example of functional dependency. So suppose I give you a functional dependency called rating determines wage. What does it mean? That means if I have a schema, let's say employee table, I have employee ID, rating, wage, and like contract ID, like department ID, and things like that, right? So that's my schema. And what I'm going to tell you is I have this constraint which states that rating determines wage. What that tells you is for different employees, if their rating value is the same, let's say rating is 3 here, then their wage, let's say this is the hourly wage they get, right? If your rating is 3, I'm going to pay you $30 per hour. The point of having this constraint is to make sure if the rating value are the same, you pay them the same amount, which is it's a very intuitive constraint, right? You don't want to work for a company where you pay this guy $30, you pay this guy $10 when they receive the same rating. If the rating is different, yes, of course, you can do that slightly different. Let's say a higher rating means a better performance. If rating is 1, yes, you can pay this employee at a lower rate. But if the rating is the same, you better pay them the same. Does that make sense? So in order to capture this constraint, we introduce a concept called functional dependency. Functional dependency. In fact, we have talked about some form of functional dependencies, right? One functional dependency, trivial functional dependency that holds for any schema is what? Is the primary key determines all other attributes. Right? Why? Because if employee ID is 1, I know the rating value must be 3. If you have another record, this must be true. And in fact, this is true because you cannot have another record with the same primary key value. Right? That's why this functional dependency is true automatically. It's automatically true. Right? Another form of constraint Another form of constraint is this primary key, foreign key relationship, right? Primary key, foreign key relationship, right? We talk about this, right? So there are different forms of such constraint in a database. So that means that this actually is a very deep topic. So I just want to give you an overview. The more detailed discussions is found in my undergraduate class. But at least now you understand what this concept is, right? Functional dependency. So what it says is, you can, at the beginning of each transaction, you do assume that all constraints are satisfied by the current database instance. Meaning, if I have a constraint like that, my database cannot have an instance that looks like this. This cannot happen. At the beginning of my transaction, if you have a constraint defined like that, I can safely assume all my instances satisfy this constraint. For example, it must be like this. You follow me? Okay? Now, a basic requirement for any transaction is, at the end of the transaction, when you commit, all constraints are still satisfied. Meaning you do not make any updates to the database that end up in violation to one or more constraints defined against your database. If that's the case, database engine should not allow this transaction to commit. For example, if you say I have a transaction, the update employee number 2 rating to $20. When you have this constraint, that transaction should not be allowed to commit. Is that clear? Okay. So a transaction is only allowed to commit when it does not violate any existing constraint defined against your database.
One with the theme last time, if the constraints were satisfied, another tuple that you had updated, it would roll back that as well, right? Not just
Say again your question.
So if there was another tuple that was updated and the constraints were satisfied, it would roll back that one as well, not just the one that
Yeah. Now, so that means that that's a basic requirement for any transaction, right? So that means that this consistency property states essentially the following. If you assume each transaction satisfies that requirement, meaning start with a state where all constraints are satisfied, and end up with a state where all constraints are satisfied by each single transaction, if you execute that in true isolation scenario, right? You just execute the transaction by itself. If that's the case, the transaction manager, when interleaving action from different transactions together,